Hello everybody, welcome back. I'm Dr. Bettina Heinz and I will teach you some more fascinating things about chemistry. Today is a little difficult one. We call it calculations based on the balanced chemical equation or stoichiometry, the measurements of weights and such relationships. And these are the topics that we will discuss today. Stoichiometry defined, it's an old term, but very important. The inspection of the molar ratio of a balanced chemical equation, which is a wealth of information for us with which we can do many calculations. A very helpful mathematical method is the dimensional analysis method, which allows us to keep track of the units. I would call it a tapeworm type of setup, that you use whatever unit conversion ratios that you need and cancel the old units and come up with a new unit, the one that you want to find out about. Remember, in science we deal with dimensions, meaning coefficient, unit, or factor label, as it is sometimes called. We will do, for instance, simple calculations based on just simple or plain mole-mole relationships, then mole-mass or mass-mole calculations, and then mass-mass calculations, which involves a few more conversion boxes or ratios, meaning a few more steps. And then we will deal with the limiting reactant problems, and we'll learn about the theoretical or 100% yield and the practical or actual yield that we can expect for a new product that we form that we're interested in finding out about. Stoichiometry is the study of the quantitative relationships based on the balanced chemical equation or balanced reaction equation, where the quantity of reference is the so-called mole that you've already learned about. Remember, the mole is a quantity which means that we have a certain amount, a macroscopic amount of individual building blocks or units, which in chemistry can be ions, atoms, molecules, formula units, or even photons, protons, etc. So the mole is the transfer ticket for us again to allow us to calculate. There are four types of calculations that can actually be made from a balanced chemical equation. We won't go into all of those, of course, but I would like to point them out to you at least, because you're going to probably take more chemistry classes, and it might be good to be sensitized to these different relationships. We will basically deal with the mass mole or mole mass, sometimes also volume mole and mass, when we deal with concentration units such as molarity. So we are basically dealing with this type of situation, which always involves the conservation law of mass. That means, remember, the atoms just recombine into new combinations. No mass is gained or lost during a chemical change. So we have grams mole ratios, milliliter mole ratios, or liter mole ratios. And the density also fits in here a little bit, because sometimes when we have only milliliters given, we have to get the grams, and that, you remember, is easily accessible by the density ratio, which relates grams per volume. So we can easily get our grams. Then we have also energy mole relationships, so we can do thermochemical calculations based on the chemical equation. So we can determine heat gained, heat lost, heat of reaction, heat of formation, etc. So we basically relate the energy unit joule with the mole. And we can also do specific heat considerations as well. Another very major part in using the balance equation for certain studies are the so-called equilibria relationships. The law of mass action falls into this category, Le Chatelier's principle. So by shifting the equilibrium, by removing or adding materials, changing concentrations, etc., we can do equilibrium studies. Here we relate mostly moles to liter or moles to kilogram. That means we're dealing a lot with concentration units, which are always symbolized by brackets of the particular, around the particular chemical involved or ion involved, etc. Then we can also use it to study reaction rates, kinetics of chemical and physical changes, phase changes, and regular chemical equations, which will deal with change in molarity per second, moles molarity per second, change of concentration with time, etc. So you see, a balance equation can help us do many, many important calculations. So we can find out about a lot of things that might be important for us and regarding of what kind of problem we are studying. So here we see the different studies that I just mentioned. Stoichiometry, the term was actually coined by a German scientist named Jeremias Benjamin Richter. I don't know if he is involved with the Richter scale, but I have to check on that. Just occurred to me. And 1762 till 1809 or 7 was his lifetime in Germany. He introduced the name stoichiometry. It's derived from the Greek for the doctrine of the combining proportions of substances. And he even did his dissertation, that means his PhD thesis, in 1789, the use of mathematics in chemistry. Of course, he expressed that in German. He later published these findings in very important articles in the years 1792 to 1794, Anfangsgründe der Stöchiometrie, or translated into English later on, Rudiments of Stoichiometry. So the word, as I already mentioned, is derived from the ancient Greek language. Stoichion means the first principle or element, and metron, as you well know, means to measure, or the measure. Metronome we find in the music realm quite a lot. And here we see again a nice view graph that shows us the central chemical equation that has to be balanced, otherwise we cannot work with it. So I hope you studied balancing equations enough. So we can study equilibria relationships, mole-time relationships, volume-mass-mole relationships, and energy-mole relationships. But we will focus on the mass-mole relationships, of course, in the realm of this class. Here we have a picture of Jeremias Benjamin Richter, who originated the term stoichiometry. Now, as I already mentioned, the method that we are using here over and over again in chemistry, in many other aspects as well, as you've already seen so far, we will use the dimensional analysis method. And I already pointed out that dimension is a number with a unit together, like 3.0 meters or 0.025 kilograms. So this is most important. Then when you deal with numerical, or dimensions rather, in science, you must always have both. Otherwise, we've lost a whole bunch of information, and just plain numbers are meaningless. So we always need the unit. So the method of calculation we are using is dimensional analysis. So we start usually off with a given dimension, and then we have the various ratios. I will just call them for fun here conversion boxes. I like to put the parentheses around them because that keeps things nice and tidy and boxed in, but you don't need to have them. So we line them up in a linear sequential fashion from left to right, and the ratios have to be set up in a way so that the old units cross-cancel, and we can set up the ratios any way we want, upside down, invert them as we need them. So we should always make sure that the units always cross-cancel, and we end up with the unit that we're looking for. Then, in the end, once we've done the inspection of the proper units, and if everything falls into place, then we can do the number crunching in the end. And that's also always a good proof that we did the right setup when we come out with the right unit in the end. For instance, let's do a little quick example. 50 milliliters of cyclohexane is how many grams? Okay, we have given 50 milliliters. Make sure you have all the figs, the significant figures involved, and stick to the rules of significant figure calculation rules or guidelines. So we have the density, which is a given ratio for us that we can look up in the literature. So the density of cyclohexane is much less than water. It's 0.78 grams per milliliter. That means 1 milliliter of this liquid on the scale measures or weighs 0.78 grams. So we see here we cross-cancel the milliliters, which I've done in orange pen, and then we multiply and we end up with grams. And we may have to make sure that we drop all the excessive units that are not part of the significance of the measurement. So that is a very important tool for us. And when we stick to this, any chemical calculation has lost its bite. So we have nothing to be afraid of. Now let's get to work and see how this business is to be worked out. Calculating with balanced equations. For instance, remember we combusted mercury in the crucible. So mercury reacted with oxygen of the environment and produced, what did I say? Mercury? No, I mean magnesium. But you could do the same thing with mercury, of course. So magnesium plus oxygen produces magnesium oxide. First of all, let's do some mole to mole calculations. For instance, I have given 0.50 moles of magnesium, and I want to find out how many moles of magnesium oxide can I produce. Well, as I mentioned before, we put the given up front, moles magnesium, and I always put subscripts of the proper chemical because that keeps track of the chemicals, at least for the beginner. And even I have to do that because better to do it, write a little bit more than to find out you have more work to do in the end. So get organized in the beginning and then you save time later on. So you don't have to check and recheck yourself that much. So here we have mole magnesium, and the ratio according to the equation is 2 moles of magnesium yield 2 moles of magnesium oxide, which is actually 1-to-1 ratio. Now if you compare that to oxygen, it would be different. But remember, you're only looking at the 2 chemicals that you want to discuss. So you only need that ratio for them. So we have the moles magnesium canceling, and we end up with moles magnesium oxide. So we did the right unit conversions already. And then last not least, we will do the number crunching. But you see here is nothing to crunch because it will be the same amount, the same molar amount. Now, how many moles oxygen are required for this? Then I set up the same. Remember, I want to react 0.50 moles of magnesium. The ratio is according to the equation. 2 moles of magnesium require only 1 mole of diatomic oxygen. So we set that up here in the ratio. The moles of magnesium cancel, and I end up with moles oxygen, which I want, and then 0.50 divided by 2 is 0.25. We got the answer. So you see, this mole-to-mole conversion or calculation only requires one conversion box, one ratio. It's the simplest form of a calculation. Gets a little bit more advanced when we deal with mole-to-mass conversions, or vice versa, mass to mole. Okay, let's see. We don't want to find out moles now. We want to see how many grams of magnesium oxide can I produce when I have 0.50 moles available of magnesium. So I set up what is given up front. Remember, I have to go from one mole to the other according to the balanced equation. So 0.5 moles of magnesium, and the ratio is 2 to 2, as we did before, as we have found out before. And then we need, of course, something more. We need grams. So the best ratio to get from moles to grams is, of course, the molar mass. I have to set up the molar mass in such a way that the mole is in the bottom, in the denominator, and the grams are in the numerator up top. So magnesium cancels, moles magnesium oxide cancel. I end up with magnesium oxide grams, or grams of magnesium oxide. I've done everything correctly, so now I can do the numbers, and I come up with 20.115, which we should round because we only have two significant figures to begin with, and the answer cannot be more exact or precise as what I originally measured. That would be magic. So this is a calculation that requires two conversion boxes. So it's a little step more advanced, as I already said. Now the next, here we have a little trailer that we want to discuss. If only 1.5 grams magnesium are needed, how many moles magnesium must be supplied? So I can rephrase my question. Don't be confused by this. Always look what is given. What is given should be up front. Then I have to go from grams to mole with the help of the molar mass, and then need the molar ratio of the equation. And here we see grams magnesium oxide cancel, moles magnesium oxide cancels. I end up with moles magnesium, and the answer is 0.037. We have two significant figures, just like the given, so we are fine. That would be correct. Now, of course, I used a little simplified atomic masses. Okay, I went a little bit too fast. Now comes the most complex problem, and that is mass-to-mass calculations. So we have to get from mass to moles, molar ratio, another molar ratio to mass of the required substance that we want to know about. 2.0 grams magnesium yield how many grams of magnesium oxide? So this is obviously mass to mass conversion or calculation. What is given? 2.0 grams magnesium are given, so they are written right up front. Now remember, right away I have to clean up the grams and get to moles. Molar mass, I can calculate that, just look up the tables of the atomic weights and add up according to the formula. So we found out that, magnesium is just an element, so that's easy. 24.3 grams magnesium is the molar mass of magnesium. It cancels, cross cancels, and we end up with moles. Then directly I go into the molar ratio because I want to get from one chemical to the other. And that only works when we do the molar ratio based on the equation. So 2 moles of magnesium produce 2 moles of magnesium oxide. 1 mole of magnesium oxide is 40.3 grams. I already calculated that. The units cross cancel nicely, and in the end I come up with grams magnesium oxide. The calculation gave at first 3.317, which is too much. We have to tailor that down to 2 significant figures, so we round. 3.3 would be the correct answer then. Another question could be, how many grams of oxygen are required? I would like to introduce a video right now, because the next the next topic that we will discuss are the gas laws, or is dealing with the gas laws. So I have some videos for you that will introduce the gas laws to you. One is dealing with volume temperature relationships, and the other will show you the workings of an atmospheric barometer. Let's see the first one, and then later I'll introduce to you the second one. Enjoy. Hi, here we are again in our laboratory, and I want to do a little demonstration about the pressure is constant, about temperature-volume relationships. And there's a nice little experiment even you can do at home. You take a balloon, you blow it up. Sure, this balloon can be bigger, but remember I have a small beaker. It's still a big beaker, but not big enough to hold a big-sized balloon. So this balloon is a containment for the gas inside. And what gas was it? It was air. I blew it up, so I also put a lot of carbon dioxide in it. Exhaled air contains a lot of carbon dioxide. Water vapor, regular air is in here. So you see, this is the volume. Remember what size it was. So I'm going to put it here into the beaker, and it has now room temperature, which is about maybe 25 degrees centigrade in here. And ice from the ice machine will be used to fill up this beaker. So I'm going to completely submerge it. Oops, forgot my ice skates today. A lot of ice around here. So now it's embedded in the ice. And we need a little time because the air molecules will have to realize that the temperature has changed outside. And what we've learned is that temperature and volume are directly related. Remember Gay-Lussac's law? So when we increase the temperature, the volume will expand. If we lower the temperature, the volume will contract. Now what do you expect will happen with the balloon in here? Well, we'll leave you in suspense for a little while. We can anticipate what is happening, but we want to see it in real life. So we're going to wait a little bit, give the balloon a little chance to contract, and then we're going to exhume it from the ice and see what it looks like. Okay, 10 minutes are up. We were going to inspect what happened to the balloon. Well, let's start. Hopefully it was a success. Put the ice out. Whoops. Here we go. Well, you remember what size it had before? This volume is considerably smaller. I would say so, and I think you would too. So that means nature is not wrong when it states temperature and volume are directly related. So ice has about 0 degrees, so of course the volume will be less. Here it is. It makes you believe in science, right? See you next time. I have to get back to work now. Yes, we have a little time between the videos, so I'm going to continue my lecture here. Notice that for mass conversions or calculations, we need 3 conversion boxes. There's one more thing I'd like to talk to you about, and that's the limiting reagent problem, very common in chemistry. That means you have to do 2 calculations to figure out which of the reactants will lead to the lower amount of product. That is what we call a limiting reactant product calculations. And that means we do the same thing with mass, do it 2 times, and then figure out whatever is less would be the limiting reactant. Theoretical yield is whatever you calculate out of your equation, and what you actually get over the theoretical times 100% is your experimental yield. And with this, I'd like to introduce to you the workings of the atmospheric barometer. We had a little problem, though. the barometer was off by about 40 millimeter mercury or something. So please consider that. It's what we call a technical error. Enjoy. We're back again in our laboratory. And today I want to demonstrate the functioning of a barometer and a thermometer. This device has both measurement possibilities. We have the barometer upstairs, and here the small thermometer, which is sufficient for measuring room temperatures. When you look up here on top, you see the mercury column in the glass tubing inside, and the top of the meniscus, or the meniscus of the mercury, is right here. So if I look at the right scale, where we have the millimeter scale, I can read off 600, here's 600, there's 700, 695. And that would be millimeter mercury, or 695 torrs. Torr is in honor of Torricelli, who invented the barometer a few hundred years ago. That's why we still honor his name. And as you remember, 760 torrs, or 760 millimeter mercury, is equal to 1 atmosphere. Now, this measurement can be more precise if we move this little slider up and down here. And it has to move so that it hits the top of the mercury column, meaning the meniscus of the mercury. And I have to turn it over to my vision, field of vision, so I can be precise. And I matched it right with the top of the mercury column. I'll turn it back. And then I can see where the lines conjoin. This is called a vernier scale, vernier or vernier, different pronunciations. And I look to see where two lines of the left and the right column, or gradation scale, conjoin or match. So let me see where that is. And I would say it's right here at 4. So the reading would be then 695.4 millimeter mercury. And that would be the pressure today. And if I look downwards, I see the thermometer, which also is based on mercury. Mercury would expand with the increase of temperature. And it has expanded, so it's up to the 81 degree Fahrenheit. Or if I look on the right side, it is 28 degrees centigrade. So I have two variables that are very handy for studying the gas laws, for doing calculations when we calculate our experimental data. So thank you very much for listening and watching the process of learning about the barometer and the thermometer, and we will see you next time again. See you next time. Goodbye.